Alright, so I would like to go into modules week 1 and cover chapter 1. So I made a PowerPoint for chapter 1, and I'm going to do all 4 sections in this one video. So chapter 1 isn't a big chapter. It's titled Introduction to Data. Right. Right. So it's chapter 1 topics. So things we'll look at: introduction to data and data types. Also classifying, collecting, organizing, and storing data. Right. So just some key concepts in relation to data. So section 1.1 is titled "What are data?" Right. So we'll look at what statistics, what's data analysis, right? So the first slide answers the question, what is statistics? So statistics is the science of collecting, organizing, summarizing, and analyzing data in order to answer questions and or draw conclusions, right? So statistics is all of these different things to help us answer questions or draw conclusions. So to make our life better, right? So and statistics is a huge topic, right? It can get very complex, right? So in this course, it's just an introduction to statistics. We're mainly just seeing, what are some key components of statistics, right? So this slide, why do we care about statistics? So statistics allows us to explore the world around us, use evidence to check whether our beliefs are true, find patterns to lead to discoveries, and share new discoveries with others, right? So it allows us to do many nice things. So for example, an application of where I can use statistics is, let's say I have 2 different courses, and in one course I'm using my math lab, and in one course I'm not using my math lab. So I could design a statistical study to see, does my math lab have an influence in success of my students, right? So it can help make my job more productive, right? More efficient. So statistics it allows us to answer questions of that sort. And then here's to keep in mind that statistics must be used carefully. Inappropriate use will result in inaccurate beliefs, and results are always uncertain, right? So we do have to have some cautions in mind when using statistics, right? And there's a lot of good books that arise question of this very topic, right? In fact, I can pull this up really quick if you're ever interested to read about this. So I think it's in here. Let's see, it should here, right? So these are some books that address quantitative reasoning and also statistics, right? So these are some really easy read books that you could read that would address those items. They're all fairly cheap. They're all written by a non-mathematician, so they're written for the general public. It's not too scientific, but the mathematics is still, content knowledge is good. They're really thin, easy read. So I would definitely check these out. I've have all 3 of these books and I've read them. They're good, right? So like, read How I Was Statistics. I mean, that's written in 1954, I believe, somewhere around there. And you can probably pick a copy up for less than $1, right? You probably pay much more for shipping than you will for the actual book, but it's a nice read if you're interested, right? So here, what we're learning about is statistics rests on 2 major concepts, right? So the first major concept is variation, right? So what variation is the difference is or changes in an item, right? So here, what I'm looking at is consider the difference between the letters O, N, and T in the following word, right? So we're looking at variation and how this cursive word was written. Congratulations, right? So if you look at just the T's, even the T's are not written exactly the same, right? The O's aren't exactly the same. The N's aren't exactly the same, right? So there's variation between these, right? There's some differences. So so we see variation every day, right, in real life, right? If you're just driving down the road, houses look different, trees look different, cows look different, horses, cars, people, right? Everything has variation in that, right? So in statistics, we care about how we describe this variation in a data set, right? And variation is, the most important concept in an introductory statistics course, right? So variation is very important, right? So I made another example of variation, right? So here is an example in exam scores, right? So let's say I have these 4 sections of statistics, and each section, I guess, had 3 people in them, and these are the test scores that they had, right? All 4 of these groups all have a mean, right, of 80, right? But it's important to see that there's different variations among all of these, right? So there's many different ways to get a sample with mean of 80, right? So it's more important to look at the variation between things, not so much just like the mean, right? So statistics isn't all about mean, median, mode. That's a very small part of stats, right? Stats is a really big topic, right? So in the second part of the major, or the second of the out of the 2 major concepts of statistics, is data, right? So data are observations gathered to draw conclusions, right? And it's really important to know that context is so important, is key, right? So here's an example where I gave you 4 numbers, right? So these could represent birth weights, millions of people, seconds in running 10 meters, right? Who knows what these represent, right? So it's important that we have units, so that way we can tell a story with statistics, right? Statistics tells a story. So data is not just numbers. We need to know context, how this data was measured, what they represent exactly, what we're trying to prove, how we collected the data, right? There's many important questions that are written in the text also, right? So the next slide talks about data analysis, right? So it's just a definition. This is the process of examining or collected data to look for patterns or numerical indicators that capture the essence of what the data is trying to tell us, right? So data analysis, right? So we analyze the data to see if we can tell the story, right? Unfold the story, right? So the next section, classifying and storing data. So we'll look at data sources and then classifying and storing data, right? So this slide's on data sources. So you can kind of think of 2 different sources of data. We can have a population of data. So this is a collection of all data values that ever will occur for a group, right? And a note here, it says often difficult to obtain all this information. So for example, if I wanted to study, I don't know, maybe I wanted to investigate if males are taller than females, right? The population would be all of U.S. citizens, right? Males and females. So that would be really hard to collect all that data, right? Not everyone's going to respond. In fact, even if I just did a study where my population was all Marian Tech students or all Marian Tech math students, none of them will ever always reply to the survey, right? It's not possible to get every piece of data, right? So what we do instead is we get a sample. So a sample is a subset of the population that we use to represent the population at large, right? And the reason is it's easier to obtain this information, and if we follow the guidance that you're going to learn in this course, it can be, you know, just as good as having the population, right? Of course, there's going to be some variation, some error, but we can use that to generalize the population, right? And again, we're always going to have variation between our samples, right? So if I collect one sample and another person collects another sample, it's not going to be exactly the same, right? But we're going to use it with statistical techniques to get a good estimate for the population, right? So that's what we're always trying to do in stats: get a sample, estimate for the population. So here's just a slide just to kind of illustrate that, right? So this blue circle is all the population, and what we do is we take a small part of that and call that our sample, right? So it's just a small part of the sample. And here's another illustration that shows the same thing, right? So all these dots are different data points in the population, and notice only some of them are being brought over into the sample, right? We only pick some. So here's an example of data sources. So suppose that we want to study for what presidential candidate A, B, or C that students at MTC prefer, right? So again, it would be very hard to survey every single Marion Tech student. You know, some people, some Marion Tech students are at the prison, some are in the high schools, some are taking online courses from out of state, some are taking evening courses, some are taking Saturday only courses, some are taking in our ASAP program like Wednesday night courses, right? It has lots of different flexibility, right? Some students may not check their email. So there's many different ways where we would not be able to get a sample of the whole population, right, to answer this, right? So there are three terms that we're look at is what is the population, who is the sample, and then what data was collected, right? So with this, the population are all Marion Tech students, right? That's who we're trying to generalize to, right? The sample is the 500 MTC students that we surveyed, right? The random sample of 500 students. Then the data that we're collecting, right, is what's your presidential preference, right? Do they prefer A, B, or C? So our goal, right, is to collect a random sample from a larger population with the intent of generalizing, right? So for example, if I wanted to find what percentage of cars in the US are Toyota, I don't know, right? I can't know that, right? But what we can do is we can collect a random sample and use it to estimate, right? To help us understand what the population would be, even though we can never know the population, right? Alright, so classifying data. So a variable are characteristics of people or things, and we have two different types of variables in statistics, right? And it's important to note that the variable here is different than like variable in algebra, right? It's not like an unknown what we're trying to solve for, right? Here, a variable are things that we're studying, right? So like for example, the first type of variable here is categorical variable. So this describes a quality or a class. So it can be numbers, but no arithmetic possible, right? So we're not, we don't want to add things together. Like so, for example, zip code is a categorical data. So anytime your data puts things in categories, then it's categorical. So you can see examples here. I have hair color, zip code, or letter grade, right? So a zip code is a categorical data. It's telling you, it's just a code to tell you where you're from, right? What city you're from, or what area you're from. Oops. And then the second type of variable is numerical, right? So this describes a quantity or measurement. So some rough examples, we can do temperature, height, length, and so forth, right? So my next slide, just want to make sure you understand that another term for categorical data is qualitative data, right? And another term for numerical data is quantitative data, right? So you should know both of these terms back and forth, as they're often used interchangeably, right? So qualitative and quantitative. Right? Alright, so I had just 5 examples just to practice going through, identifying the population, the sample, what variable we're interested in, and then also what type of variable do I have. Is it quantitative? Is it qualitative? Right. So the first example, right, says Fox executive is interested to know the average age of the Fox viewers. To test her hypothesis, she samples 200 Fox viewers at random and determines the age of each. Right. We want to identify. So the population, right, would be all of the Fox viewers. Right. The sample is the 200 Fox viewers chosen at random. Right? That's what our sample is. The variable interest is age, right? That's what we're trying to measure, right? The type of the variable, so age is quantitative. So we can say quantitative or numerical. Right? And then number 2, so it says, I was concerned about the average height of MTC female students. I randomly selected 34 female students and measured their heights. Identify, right? So this is a much smaller sample than 200 from the last, but nonetheless still a study, right? So the population here are all of the MTC female students, right? We're not talking about all students, only the female students. So the sample are the 34 randomly selected MTC female students, right? The variable of interest is height, and this is quantitative or numerical, right? Type of variable. Right. So here's another couple examples. So here we have the U.S. soccer coach is interested to determine the average annual income of soccer players in the country. He randomly selects 30 soccer players and asks their income, right? So the population is all of the soccer players in the U.S., right? It says U.S. soccer coach, and he's interested in the soccer players in the country, right? So we're only talking about the U.S. The sample are the 30 soccer players chosen at random. The variable of interest is annual income, right? And the type of variable is yet again quantitative or numerical, right? Good. So then there's another one here that you can try on your own. And there's also a 5th one you can try on the next slide. So practice that and see if you can identify the population, sample, variable of interest, and the type of variable. Actually, in all these examples, they're all examples of quantitative or numerical types of data, right? So qualitative is also important. I mean, as a mathematician, I focus on quantitative data, but qualitative data is also important. Anytime you put things into categories, right? Right. So here's another example, right? Let's say you want to do take information on Marian Tech students, right? So this is the type of data we're going to collect: their name, their gender, their age in years, and then also their age, and you're breaking it into these 3 categories. And so sometimes when you work with data, categorical data, you code things with numbers, right? So if we give a 1, that means that the person is 17 years and younger. If they get a 2, they're 18 years old, and if we code it with a 3, they're 19 years and older, right? So this would be categorical, but we are coding it with a number, right? And then we're collecting their ACT score, their high school GPA, and then what state they're from. Are they from Ohio or a state other than Ohio? And again, we're coding this with a number. Right? So the name would be categorical or qualitative. Same with the gender, right? Either male or female, categorical or qualitative. The age in years would be an example of numerical or quantitative data. But the age here, how it's listed with the 3 groups, right, would make it categorical or qualitative. And then ACT would be numerical or quantitative data. Same with high school GPA. But then lastly, the state variable would be categorical or qualitative data. So here's an example of data collection, right? So this is just looking at one particular case. So we have John Smith, who's a 19-year-old male, and since he's 19, he'd be coded as a 3 for age. He got a 22 on the ACT, a 3.4 high school GPA, and he's not from Ohio, right? So he gets coded as a 1, right? So this is just specifics for one person. And then on the next table, I'm showing you how we can organize our data, right? So this is an example of what we're going to learn, what's called stacked data, right? So each row is one particular person, right? In each one of these columns is a statistical variable, right? So John is a male, right? John is also not from Ohio, right? So he got 1, right? So all of these information in the column is information about John, right? So this whole row is nothing about John. Like here's Brad, right? Everything in this row is all about Brad, right? So he's 22 male, 25 on the ACT, 3.01 GPA. He's not from Ohio, right? So this is what we would say we have 7 cases, right? There's 1, 2, 3, 4, 5, 6, 7, right? There's 7 people, 7 cases or observations. But we have 6 variables, right? Our variables would be gender, age, ACT, high school GPA, and state, right? So 6 variables total. Right. So here's a little more information on the stack data, right? So as I was saying, we store the data values in like a spreadsheet format where each row is by person, right? And the benefit of this is we can store many variables, right? I can have as many variables as I want about each particular person, right? In the next slide, we'll look at an unstacked way to store data, and it makes it very hard to have many variables in that fashion. In fact, you really can't, right? So here's an example that was also in the book where each row corresponds to one infant, and we're able to record their birth weight, what gender are they, and then also if they smoke or not, right? And notice, like here on this top row, we have a new infant that's 7.69, probably pounds, maybe ounces, right? I'm not sure of the unit, right? So it's always important to identify units, right? And maybe in a write-up of your study and whatnot, right? You want to identify what every variable is, how it's recorded, and so forth, right? And then like here with the column female, so typically we use 1 to mean like yes, right? So in other words, this first baby got a 1 for female, so that means they are female, and 0 typically means no, right? Or that they're not in that category. And the smoke is the smoking status of the mother, right? So the very first child had a weight of 7.69, guessing pounds, right? Was a 1, so was a female, but their mother did not smoke, right? So that's how you'd interpret that first row, right? And then the next slide is talking about unstacked data, right? So here my data values are stored in 2 columns. and each column is a variable from a different group, right? So we have men's height and women's height, right, as our example. So we can only store data for two variables then. We can't have multiple, right? And also the rows are different, right? So like this row of data, 70, 59, those don't go together whatsoever, right? Every cell is a new person, right? So there are 4 women here and 3 men, right? All right. So now we're ready to go into section 1.3, which is organizing categorical data, right? So why organizing is important, and also to look at something important called two-way tables. So why do we need to organize data, right? So raw data is data as it's collected, right? It's not put in a nice table or whatnot, right? And sometimes some researchers will call something raw data when it's really not, right? So we're going to look at an example of that, right? So a couple of slides will talk about two-way tables. Some people refer to two-way tables as raw data, but that's not raw data, right? Raw data is how you collect it, right? So it's like your Excel spreadsheet of all your data, right? So that can be very messy, hard to read and understand, and also hard to see the patterns, right? You might have 2,000, 3,000 pieces, different respondents. It's a lot of data, right? Maybe 10, 12 variables. It's hard to see the patterns, right? So organizing the data can help us see the patterns, but organizing is not always so easy, right? So here you can see one way to organize data is to do a two-way table, right? So it's a very common way to organize data. It's able to display results from two potentially related variables, and then also shows combination of the various variables, right? So we'll look at an example here in a moment, right? So this next slide is an example of some raw data, right? So this column of ID, so this is like person 1, person 2, person 15, right? So it's very common statistics to your first variable to be ID, right? So we name every person, right, a number, right? Typically, we probably wouldn't keep track of their name and so forth. Maybe you would. It's hard, depending on the study. And then here we have variable gender, right? So we're identifying is it male or female, and then this variable, the seatbelt usage, right? So do they always or not always wear their seatbelt? So then here is a two-way table example, right? So taking that raw data and throwing it into a two-way table, you would get this table, right? This is called a two-way table. So how do we get like this 2 number, right? So you'd want to look how many males answered not always, right? So if we go back to the raw data, right, how many males answered not always, right? So we have 1 here, right, and 1 here, and that's it, right? So you just count how many people fit in those categories, and you would do that for everything, right? For the male not always, for the male always, for the female not always, and the female always, right? So my variables here are gender, male, female, and then also whether or not you wear your seatbelt. Yes, you always wear it or not always, right? So two-way table, you want to have 2 different variables split in 2 groups, right? So you have 4 rows and 4 columns, right, of your, or excuse me, 2 rows and 2 columns of your data, right? So four cells of data. So the table can tell us, that there are 3 males who wore a seatbelt, right? Always wore a seatbelt. We have 10 females, right? If we add, so here these are all females, so 3 plus 7 we get 10 total. And then we have 5 people total who do not always wear a seatbelt, right? So if we total this way, 2 plus 3, we get the 5, right? So I just did some interesting calculations here really quick, right? So if we look at the female, we have 10 out of 15 total, right, are female. So 2/3, right, are female, and 1/3 are male, right? So 5 out of 15. If we look at not always, so if we look at the one not always, 3 out of 5 total, right, who reported not always were female, right? So the majority of people identifying not always were female in this case, 60%. And then lastly, 7 out of 10 or 70% of the females reported always wearing their seatbelt, right? So 7 out of 10, right? This 7 out of 10 total reported always wearing their seatbelt. Right. So this next slide gives us caution for incomplete data, right? So the caution is, even when the data looks complete, crucial information may be missing, right? So here's an example where we're given sport and the number of injuries, and it says, given the data in the following table, which sport listed is the most dangerous, right? So if we look at this, the number with the highest number of injuries is basketball, right? Which seems surprising, right? Basketball would be more dangerous than football or ice hockey, and so forth, right? Seems surprising. But what we're missing is maybe how many people are in every group, right? So if tons of people play basketball, then of course the number of peer injuries are going to be a bigger number than the others, right? So one thing we might want to look at is what's the percentage of people that participate in the sport that get injured, right? So here, we're missing critical information, right? So we need to know the total number of players, and then how common are injuries among all of the players, right? So if I play basketball, what's the percentage of people that get injured? How likely is it to happen? So this slide gives us some more information about that, right? So when we compare groups, the groups need to be similar, and also we need percentages or rates to form better comparisons, right? So here we have our sport column with our different categories. Here are the number of participants in each sport. Here's the number of injuries, and then here's the rate of injury per participant. And then lastly, to make these numbers easier to work with, we scaled this to 1,000, right? Rate of injury per 1,000 participants. So it's easy to see that football is the most dangerous, right? It has the highest rate of injury per 1,000 participants, right? So more people get hurt in football than the other sports in comparison, right? So you can see that in football, only like 8.9 million people participate, where in basketball they had over 24 million. So, about 3 times as many people play basketball than football, according to this data. So of course they had more people getting hurt, right? But if we look at the rate, right, the basketball rate is nearly, less than half of what the football rate is, which makes more sense. Right? Surprisingly, the ice hockey rate is very low, right? 6.14 per 1,000. Right? That's shocking to me. So more people get hurt in baseball than ice hockey, according to this data. Right. So then the last section, 1.4, talks about collecting data, understand causality, and also standards of a good study. Right. So studying causality. So causality is what causes something to happen. So it can be understood in terms of 2 variables. We have a treatment variable, so did the individual receive the treatment or not, right? Then the outcome or response variable is identifying if that person had the response happen, yes or no, right? So the goal is to be able to determine if the treatment variable causes a change in the outcome variable, right? Right, so here's an example of causality. So let's say you want to know whether a certain diet aid works. You would record If the diet aid was given, right, that's the treatment variable. So, yes or no, did you receive the diet aid? And then the results of the weight loss would be the outcome variable, right? Did you lose weight? Did you not lose weight? How much weight did you lose, right? Outcome variable. And then the next set of terms we have to talk about are treatment and control groups, right? So the treatment group is a group that receives the treatment or has the characteristics of interest, right? So sometimes the treatment group, the participant is choosing the treatment. So for example, did they choose to smoke or not smoke, right? That picks what treatment group that they're in. And then the control group is the group that does not receive the treatment, right? Or at least does not have the characteristic of interest. So if you're trying to measure, if someone smokes, do they run a 400 meter slower, right? So the control group would be those that that are not smoking, right? If that's your treatment. So then also talk about a placebo, right? So a placebo is a harmless pill or lookalike given in place of actual treatment, right? So for example, let's say you're giving some medicine in in some study to see, does this medicine help improve ADHD, for example, right? So you don't want one group to know what group they're in, right? Or you don't want them to think one group is being treated differently than another group, right? That can hurt your study. So what you want to do is if you give one group a pill, you want to give the other group a pill also, right? But to be able to test to see if this pill works, one person would get a placebo like a sugar pill, another person would get the actual pill, but they would look the same. One would contain medicine, one would just be sugar, right? So you may have heard of this in like psychology, right? And then also something we have to take into consideration is the placebo effect, right? So sometimes people react like they're receiving the treatment when they're really not, right? So for example, you're saying that this medicine helps ADHD. So if you give someone a placebo, the sugar pill, they might suddenly have better attention, and it's more of a mental thing. They're thinking that they're receiving the treatment to help them, right? So then the next slide is good practices in studying causality. So we can have a controlled experiment, which is where the researchers assign subjects to a treatment group, right? This can show causality. And then also a random assignment is where we randomly pick subjects to be in the subject group, in the treatment group, right? So assignment, we can use technology to do this, and that helps tend to give us more randomized pairings, so that way it balances out the differences in the groups to minimize bias, right? So we can never get away from bias, but we do want to try to limit bias. So another good practice in causality is blinding, right? So blinding is where the independent party assigns subjects to a treatment group, right? So the researcher or the subjects don't know what treatment group they're in, right? And then double blinding is where the researchers also do not know who's in the treatment group. So double blind is the best scenario. So that way the researchers don't treat different people differently, or maybe record results differently and so forth. And then we also don't want the participants to know what group they're in, because then they might act differently, right? So we want to try to do this to really see what's going on, right? So other types of studies that can occur, anecdotal evidence. So this is a story based on someone else's experience. So for example, maybe someone is the first law student, maybe first female law student at a particular university, right? So they could write a narrative describing this experience, right? But this is anecdotal evidence. It's not something we can generalize, right? This is one data point based on one person. So we can't really do something statistical with this quantitatively, but this would be like a qualitative type of research, an anecdotal research-based study. So it's not not necessarily that anecdotal is bad. We just can't do quantitative analysis with it, right? Um, and then also an observational study is where subjects are placed in different groups by choice or someone else, right? And they're observing observing the study, right? It's not a controlled study. So here we have caution. So anecdotal evidence and observational studies. So we can never use these for cause and effect, for causality, right? They can only point to association between variables, right? So we have to keep that in mind if you're working with this type of study. So to establish cause and effect, we need to have controlled experiment, right? But that's not always possible, right? So other ways of studies can be appropriate. So here's an example of causality. So if you notice that when there are long lines going to the beach, the number of ice cream sales go up. That does not mean that the long line to the beach are causing the increase in ice cream sales, right? So this is an example of an observational study, right? So just because there's long line does not lead to long lines to the beach does not mean that there's going to be increase in ice cream sales, right? So here what we have to consider are confounding variables. So confounding variables are variables that have not been accounted for, but which is causing a difference in the groups being studied, right? So for example, in the previous example, a possible confounding variable could be the temperature outside, right? So the temperature outside could influence the increase in ice cream sales, right? Right. So then this next slide is the gold standard in experiments, right? So the gold standard in experiments are to have these four things where possible, right? So we want to have large sample size, so we can really account for that variability, right? We want the assignment to the treatment or control group to be random and also controlled by the researcher, right? We want to control in the sense that the variable that we're trying to study is the only difference between the two groups, right? Everything else we try to keep as much alike as possible, right? Then also, if appropriate, use a placebo, right? Make both groups treat them the same way with quotes, if you will, right? So if one group gets a pill, the other group needs to get a pill. Although one would be medicine, one would be a sugar pill, right? They might not necessarily mean they both get the treatment, the same treatment, but they're getting it appears like a third party would appear it as being the same. And then also, having a double-blind study is a gold standard in experiments. Right. So in the last slide I have for us was statistics in the news. So when you see statistics in the news, you should always ask yourself a few questions, such as, right? So one, is this an observational study or a controlled experiment, right? Number two, for controlled experiment, did it meet the gold standard, right? So the previous 4 gold standard. Number three, was the paper published in a reputable peer-reviewed journal, right? So a reputable peer-reviewed journal is a journal where not anyone can just submit an article to be published in the in the journal. So a peer-reviewed journal is where a group of peers, so for example, if I want to publish in a statistics journal, then a panel of statisticians, right, would be the peer review, and they would review my article and critique it before it could be published, right, to make sure that it's high quality and that it's a good material, right, something that's truly publishable and everything is very sound, right? Um, and then number 4, did the study follow people for a long time, right? So you want to think about the length of time also with that, right? All right. So that's all I have for chapter 1. So that should get you through working on those assignments. If you have any questions, feel free to email me. That's all I have.